Hello everyone. In the previous video we talked about electron configuration. Right now I want to extend that to orbital notation. So orbital notation has its uses. It's a little bit more cumbersome to use, but it's nice to see it. It's nice to see patterns in bonding with orbital notation. So again, let's start off with the oxygen's electron configuration. That's 1s2. 2s2p4, okay? And we find that with the electron's electron configuration, we can now translate that to orbital notation. And orbital notation says that for every every sublevel has a certain number of orbitals. And if you remember, S has 1 orbital, P has 3, D has 5, F has 7. And they look like we're going to draw them like this, okay? We're drawing this horizontal dashes. Okay, where 2 electrons, we draw them as half arrows. You can draw them any way you want. We draw them as half arrows, so like that. Okay, so notice S can hold a maximum of 2, just like we did before. P6, D10, F14. Okay, so as far as orbital notation goes, if I'm going to translate this down, it's going to look like this: 1s2, 2s2, P. You got to draw them all, and the way this works is every orbital gets an electron, and then if you have extra, you double up. So watch. 1, 2, 3, now double up, 4. Okay? This is wrong. That's wrong. You have an empty orbital, that doesn't work. Okay? That's not what we see. Okay? All right, so when we take a look at aluminum, again, very similar. Let me get rid of some of this stuff here. Take a look at aluminum. 1s2, 2s2, p6, 3s2, p1. Okay, I believe that's what it is. Yes, okay. Now, the orbital notation is 1s2. Again, pause the video whenever you need to. Draw them all. You got to draw all the lines, and you must draw the lines. Don't leave just blanks. P1, done. Okay, so notice this is 1s2, this is 2s2, this is p6, this is 3s2, this is p1. That's a little sloppy, but you see it. Okay, and the orbital notation for vanadium, let's just jump in there. That's 23 electrons. Okay, so without doing the electron configuration, let's just do the orbital notation. It's 1s2. We'll try not to make you do the big ones. 2s2, p6. 3s2, p6, 4s2, whoops, 3d, 1, 2, 3, 4, 5, yes, draw them all, but I only need 3 electrons, so put them in the first 3. Okay, according to Hund's rule, the electrons will occupy the lowest orbitals that receive it, and those are the lowest ones. That's 23 electrons, okay, and as I mentioned here, I mentioned it previously, anytime you're going to lose electrons from the highest, you're going to lose them from the highest occupied energy level first. I think I needed to delete that, but that was on the previous slide from the last video. Okay. Okay. Now, noble gas notation. This is for the big ones. Actually, they use this a lot. For example, if you did titanium, titanium is element 22. So it's going to be the electron configuration is 1s2. 2s2p6, 3s2p6, 4s2, 3d, I think it's 2. 3d2, yes. The noble gas notation says we're going to do this. You're going to go to the period that titanium is on, and titanium is on period 4. Go back to the previous period, okay? So you're going to start off with the previous period's noble gas. That's the period 3 noble gas. Period 3 noble gas is argon. That takes care of 18 electrons right there. That's why this is a shortcut. Argon has 18 electrons. There's 18 electrons there. Okay. Now go back to where titanium is. It's on the 4th energy level. It starts off with the S block with 2. Now I have 18 plus 2 is 20, and now I just need 2 more, 3d2. Okay, so once you get back on track and you go to 4s, now just follow electron configuration again. Notice these absolutely match. They match. These are called inner shell electrons or core electrons. They're typically involved in things like called the shielding effect. More on that later. These are typically you're going to be involve your valence electrons, but not always. There's some extra ones in there, especially in this case. Okay. Let's jump down to cesium. Cesium's huge. Okay, so what you're going to do is if we do the electron configuration, this is a pain in the butt to do this every time. Oopsie, why did I go to 3? 4p6, 5s2, excuse me. 4d10, 5p6, 6s1, okay? 6s1 all the way down there. Yeah, that's terrible to write. So what we would do is find cesium. It's on the 6th period. You're going to go to the previous period's noble gas, which is xenon. That takes care of 54 electrons, okay? 54 electrons. Cesium has 55. So let's just go back to what cesium's on, the period it's on. It's on the 6th period. You always start off with S. I just need 1. Notice 6s1 matches this. That means all these are inner shell electrons or core electrons. That's your valence electron right there. You're done. Okay. Okay. And just to kind of follow up here and to finish before we move on to something a little bit different, if you hear the word main group elements, that's the S and the P blocks together, the S and the P block electrons together. Okay. Transition metals, those are groups 3 through 12. Valence electrons are the outer electrons available to be lost, gained, and shared, and that's in bonding. Okay. So valence electrons are the electrons found in the main group elements. Okay. It's the S and P block. Okay. They're called the valence electrons, and they're found in the S and P block. Main group elements only. Notice I did mention those are the main group elements only for this comment right here. Core electrons are inner shell electrons. I've already mentioned that. They're the electrons inside the highest occupied energy level. So these are all inner shell. Here's the highest occupied energy level. These are the core electrons. Shielding effect describes the decrease in attraction between an electron and the nucleus in any atom with more than one electron shell. So basically, the more core electrons you get, the more the shielding effect happens. Okay? The shielding effect is essentially shielding or blocking the effective nuclear force from the outermost electrons. So the more shells you have, so if this is your nucleus, which is called NUC for nucleus, if I have one shell, there's so much shielding effect. So here's my outer electrons. If I have a second shell, there's even more shielding effect. If I have a third shell, there's more shielding effect. So these are held looser and looser and looser every time I put a shell in. Okay, and then you can read what paramagnetic and diamagnetic are. Those are unpaired electrons in the outer shell. Diamagnetic are everything's paired in the outer shell, and I'll talk about that in class. Okay, if you have questions, email.